Okay, let's look at a couple of examples now of discrete time Fourier transform of some common signals, sequences. Let's consider first just the shifted impulse located at k. So that's what that would look like in the time domain. We've got a discrete time impulse, which remember has a perfectly finite height, is not infinite in value, and so we can compute the Fourier transform from the definition x of n e to the minus j omega n. Of course, x of n is 0 everywhere except at n equal to k, where x of n is equal to 1. So all other terms in the summation except the n equal k term will be 0. So we're left with just e to the minus j omega k as the result of the Fourier transform of the shifted exponential. So the magnitude spectrum would just be equal to 1. That's the magnitude of this. The phase angle, the phase spectrum, would just be equal to minus omega k. So it's a linear function of omega. So both these are pretty easy to plot, usually over the interval from 0 to 2 pi, and in this case the magnitude spectrum or amplitude spectrum is just equal to 1. The phase spectrum would look like this. It's just a straight line, would have a negative slope. This is our frequency variable, omega. So the slope of the line would actually depend on the value of k, which is the delay in the impulse from the origin. Just also note as a special case of this, note that the discrete time Fourier transform of an unshifted impulse is, we just let k equal 0 in this result, is just equal to 1. So that would have the same magnitude spectrum. Phase spectrum would just be 0 because the slope of this is minus k. In this case, with k equal to 0, the slope would be 0. Let's look at another example of a slightly more complicated sequence. Let's let x of n be equal to gamma n u of n. Okay. So what this would look like at n equal to 0, gamma to the 0 power would be 1, and then at n equal to 1 we would have a height of gamma. So I'll draw this assuming gamma is less than 1. At 2 we have gamma squared, at 3 gamma cubed, and then so on and so forth. So this will be the x of n sequence, and since we're multiplying by the unit step for all the negative n values, the sequence would be 0. And so I've sketched this now for gamma less than 1, so we've got a decreasing sequence. From the definition of the discrete time Fourier transform, it's the sum from n equal minus infinity to infinity of x of n e to the minus j omega n. This is reduces right away to, again, x of n is 0 for all negative values of n, so my lower limit becomes 0, and for n in the range from 0 to infinity, x of n is equal to gamma n. and I can actually combine these two terms, since they're both to the n power. There's gamma e to the minus j omega, all to the n power. And now I'm going to use one of the formulas from my summation table, which you'll find in the textbook. It was also on one of the handouts, one of the early handouts provided in the course. But the sum from 0 to infinity of a to the n is 1 over 1 minus a, as long as the magnitude of a is less than 1. So using this result, we can write that x of omega is 1 over 1 minus gamma e to the minus j omega, as long as gamma e to the minus j omega is less than 1, or the magnitude of gamma is less than 1. It will converge. It's a little tough to get the magnitude and phase in this form, so I'll actually use Euler's formula to rewrite that exponential term as 1 minus gamma cosine of, it would actually be minus gamma because of the symmetry. I can just write cosine of gamma, and then I'll also have minus gamma sine of minus, but that will become plus, so I'll have plus j sine, and I forgot my gamma term, sine of omega here. And so now I've got it written in this form. I can find the magnitude. It's the square root of the sum of the squares, so that would be square root of 1 minus gamma cosine of omega squared plus gamma squared sine squared of omega. And I can multiply this term out and simplify a little bit. I'll get a gamma squared cosine squared plus a gamma squared sine squared. That will become just a gamma squared minus 2 gamma cosine of omega. For the final result, for the magnitude spectrum, the phase spectrum is a little easier to come up with the formula. The angle of the numerator is 0, and so subtracting the angle of the denominator is the inverse tangent of the imaginary part, gamma sine of omega, over the real part, 1 minus gamma cosine of omega for the phase angle. A sketch of those would look something like this for the magnitude spectrum. Again, here I'll sketch it over the interval from minus pi to pi. You probably want to verify this actually just sticking in values into your calculator or using MATLAB. It would be a lot easier to plot, and I'll sketch it for the particular case where gamma is equal to 0.8. If I plug omega equal to 0 into the formula with gamma equal to 0.8, this has a peak value of 5 at omega equal to 0. So this would be plus pi, and it looks something like this. And don't forget that this is always a periodic function, so it'll return back up to 5 at 2 pi, and then just repeat periodically in both directions. The phase function is a little tougher to plot. You probably want to stick in, evaluate the phase at particular values of omega. It is always going to be periodic as well, and it looks something roughly like this. this is periodic, so we continue on across 0 again at 2 pi, and the peak value is almost 60 degrees. Okay. You can find other transforms in the table in your textbook. I'll also provide a handout of discrete time Fourier transforms for your convenience.